Figure 10 shows an arrangement of gears. Each gear turns around a fixable axle, so just like a pivot. Gear P is turned through one complete revolution per second. So basically, it's turned, let's say the starting point, it turns all the way back once round. Which of the following describes the motion of gear R? So if this is turning this way, then this will force this one down this way, which will force this one that way. So this will move in the same direction as this one. And also, if, for example, we were turning this one once, because it's got so many more teeth, you can imagine this would move significantly more times than this one, okay? But because this is the same size as this one, the same number of teeth, it will move the same number of times. So one cycle here, one cycle here. So speed or revolutions per second, it would be the same as... It would be same as P, because that's turned once, so this would be once, and the direction would also be the same as P, so you get that. Also, the ratio here is one turn of this, because this has 10 teeth and this has 40 teeth. If this goes through 10 teeth, you only move this down by 10, or a quarter of its way, only 10 teeth as well. So one revolution of this will be a quarter revolution of the big gear, which will also end up as one revolution of this. If you were to turn this one turn, it would basically move this one 4 times round, because you have basically four lots of 0.25, which equals 1. So another way of expressing this ratio would be 4 to 1 to 4. So 4 turns of this would result in 1 turn of this, but 1 turn of this would result in 4 turns of this. Figure 11 shows the same arrangement with gear R replaced by a rack. The rack can move up or down when the gear turns. The teeth on the rack are 2 millimeters apart, so 2 millimeters apart here. Calculate how far the rack moves when P turns through one complete revolution. So this will move 10 spaces here, this will move 10 as well. So you're just multiplying the distance between each teeth by the number of teeth that are moved along. So if 10 are moved down, you just do 10 times 2, which is 20 millimeters. Pretty easy. For these questions, I kind of find it easy to almost visualize these things actually mechanically moving and just imagining what's happening as a result. So you're sort of seeing these animate in front of your eyes, and that kind of helps me work these out. Figure 12 shows 3 toy animals hanging from a rod. The rod hangs from a ceiling by a string tied to the center of the rod. The system is in equilibrium, meaning it's balanced. So this is a question about moments. Use the principle of moments to calculate the mass of the toy element. So remember, a moment is the force of the object hanging or on the seesaw or the lever multiplied by the distance. Now, this one you can keep in centimetres because they're all in centimetres, so it doesn't really matter. I mean, normally they give it in metres, but this is in centimetres, and because they're all the same, you can keep it in centimetres. So to work out what you want to make sure is this is balanced. So firstly, you have to work out the anti-clockwise moment. That's the moment acting in this direction. So anti-clockwise. This is the clockwise moment because the elephant is moving downwards like this. So you'd have to work out 15 times 6 plus 4.6 times 10, and that will give you the anti-clockwise moment, and that will equal whatever this is. So let's see how we do this. Clockwise moment equals anti-clockwise moment. That's the first thing you need to know. Moment equals force times distance. So the duck has an anti-clockwise moment of 46 Newton meters, or Newton centimeters rather, and the rabbit has 6 times 15, which is 90 Newton meters, and so the anti-clockwise moment is 136 Newton meters, and that has to be equal to this because they are in equilibrium. So you now have to do a rearranging. So you know that 136 equals 17 times whatever the mass of that is. So now we just rearrange the equation. So 136 divided by 17, remember this side has been multiplied by 17, so to get rid of it on this side you divide by 17, and you must do the same to the other side. So 136 divided by 17 will give you 8 grams, and you could check that because 8 times 17 should equal 136, which it does, which equals that. Nice, actually this is quite a nice question for 4 marks, because if you just follow it through it's quite easy to get 4 marks. Figure 13 shows a diagram of a device for lifting heavy loads. So this is a hydraulic system using fluids to lift things. The metal tube is filled with oil. The piston Y is pushed down with a force K, and this produces a force L on piston Z. The pressure exerted on the oil by piston Y is the same as the pressure exerted by the oil on piston Z. So in other words, the pressure here between this piston and the oil here is equal to the pressure by this fluid on this piston here. Explain the difference between the size of the force K and the size of force L. So if you take your time with this one, it's also quite nice and easy. You need to remember that force or pressure is force divided by area. So another way of expressing that is force equals pressure times area. And if you figure that out, then it's quite easy to understand. You don't have any figures here, so you're just using a mathematical equation to explain what's going on. So if we know the pressure here at these 2 points is the same, but we can obviously see the surface area of this piston is much smaller than the surface area of this piston. Mathematically, it stands to reason that if you multiply the same pressure by a bigger area, the force will be greatest where the area is biggest. Mathematically, that works. So the only thing that's varying in this is this value here. If this is greater, this will be greater. And that's what we have to explain. Pressure is same on piston Y and Z. Surface area of piston Z larger, so force L larger than force K using that formula there. Nice and easy once you work it through mathematically and logically.